to AWS On Air. We are at Reinforce, and I'm really excited for all the guests that we have on today's show, as well as the guests that we're having throughout Reinforce. My name is Marie. I am a partner solutions architect, been with AWS for a while, and I'm joined by the amazing co-host Jeff. Jeff, why don't you tell us a little bit about yourself?
Yeah, hey everyone. My name is Jeff Marushak. I'm a senior solutions architect on AWS's DoD Air Force team, and it's great to be bringing some of these demos to all of the customers who are here at Reinforce in 2022. So, you know what? Let's go ahead and let our first guest introduce herself.
Hi, Jeff. Thank you. My name is Ana Simões. I'm a principal specialist for AI ML at the ML Frameworks team at AWS. I've been at AWS for 10 months now. I'll let my co-presenter introduce himself.
Hey, thanks, Anna. This is Kawaljeet Kurmi. I'm working as Senior AI ML Specialist Solutions Architect. I'm with Amazon Web Services for almost 3 years now, and I specialize in containerization and machine learning applications. Excited to be here. Thank you.
And my name is Alex Jankowski. Nice to meet everyone. I'm a principal solutions architect for self-managed machine learning, and I specialize in orchestration of machine learning workloads on AWS using containers.
Amazing. We have some great guests. I am excited to learn a ton from all of you today. Definitely some spaces I could brush up on my technical knowledge. But yeah, why don't you kick us off? Why don't you tell us a little bit about distributed training and why we need it, what it's for, all the things in between?
Of course. And in my team, we see a lot of customers working with machine learning and AI, and we're finding that a much broader application across industries and use cases as varied as language models, autonomous agents like self-driving cars and robots, genomics, medical imaging, even financial markets and robo-investors. So a very, very broad adoption of machine learning and AI across all industries. And for machine learning in general, and specifically for deep learning, performance of the final system tends to increase with the amount of input data provided, also with the size of the model that you produce. And the size of the model we measure in number of parameters. Now, the ability to process larger data sets and produce large models is, of course, bound by the underlying compute, and specifically by the amount of memory you have to code that input data and the model, also about the amount of processing you have, right, which will define how quickly you can go through that data. And in distributed training, the workload of a model is split and shared among the multiple processors, which we call worker nodes. Also, the data itself, the input data, is shared across those multiple nodes so that you can keep all of the data in the system. And these worker nodes then work in parallel to speed up the model training. And that type of distributed machine learning improves performance, increases accuracy, and will scale up to very, very large data sizes, right? It also will help in producing very large models, which for certain use cases like language models can be a very determining factor for improving performance, like GPT-3, for instance.
Awesome. Okay, I'll pause for a second. Jeff, did you want to take the second question?
Sure. Yeah, sorry about that.
Okay. No, you're fine. So we'll count down 3 seconds and then go ahead and jump in.
Yeah, so what challenges are customers facing with scaling these machine learning jobs when you have such large data sets and not to mention large models?
Yeah, I'll take that one up. So I think it's proven today, right, that if you want to achieve better accuracy, you need to go with significantly large training data set and use large machine learning models. Now, when you're training your machine learning models or a deep neural network with a significantly huge data set, it actually takes a long time. And that actually means your time to market increases as well, because every training iteration, you'll have to really wait for training to finish. And then you decide whether there is any optimizations or enhancements you can tune in the next training run. And if you want to do it efficiently, you have to make sure that your underlying compute could be scaled out and you could train those models and parallelize it across multiple different GPUs. However, when you do that, you need to actually maintain or work on the overheads that these machines, which are underneath machine, communicating with each other, right? So and it takes a lot of work, and it's pretty complex. And secondly, we talked about the large machine learning models, right? And they're so large today with billions of parameters that they sometimes just could not fit into one single GPU's memory. And then you'll have to adopt techniques, right? Model parallelism, where you have to split the graph of the model across different GPUs, which is very time consuming, it's complex, and it's very inefficient procedures. So yeah, a lot of time goes in really ensuring that the data parallelism and the model parallelism could be done efficiently, while at the same time you're able to utilize your underlying infrastructure in the most optimized way.
That's
And
awesome.
it's probably safe to
So-
say that training never stops, right? You're always going to be training. So
Exactly.
Yeah, no, definitely. And like, I am so excited for the demo later and to see this all in action. So how do our
I'd like
customers
to add a
leverage?
couple of points to this answer. Kanwal put it very well that we actually have the challenges of the large model data sets and models, and we tackle those with distributed data parallelism and model parallelism. However, a couple more challenges are that we need to make sure that training is resilient and also cost effective, because these large models nowadays, when you're training billion parameter models, it is not uncommon to have to spend more than $1 million for a single model training. And resiliency is also very important, because what happens if one of the training nodes fails in the middle of the training? Do you have to start over, and you've already spent perhaps days training the model, and you don't want to be able to lose all of the work that has done. So these are normally tackled by checkpointing your model as you do the training, and using frameworks like PyTorch distributed elastic, or the PyTorch training operator, which we'll see a demo of later. And in terms of cost, there is a lot that we can do to do cost optimization as well, including there are some very cost efficient and performant instance types that Amazon offers for distributed training, like the Amazon Trainium instance that is coming up, like the Habana Gaudi based DL1 instances, which are alternatives to GPUs, also various types of GPUs that are offered in the accelerated stack on AWS.
Yeah, no, that's awesome. And thanks for sharing, Alex. I love these teasers for our demos here in a bit. Yeah, so one quick question before we jump into demos. So how do our customers leverage Kubeflow and SageMaker for distributed machine learning training workloads? I know I hear those both all the time, but just wanted to hear a little bit more about it.
Yeah, like you see, right? Distributed training is kind of something which everybody is trying to adopt to train these big and complex models. And there are many open source solutions that allows you to do that, and that comes inbuilt with the deep learning frameworks like PyTorch, DTP, TensorFlow, multi-worker mirror strategy, and frameworks like HorrorWord, which works with PyTorch and TensorFlow and MXNet. Now, customers brings in their model, and they need kind of a shared cluster which could scale up and provide them with a lot of GPUs. And that's where they tend to use open source container orchestration solutions like Kubernetes. And we have a managed service at AWS called AWS Kubernetes Service. And they use Kubeflow as a machine learning toolkit which sits on top of the Kubernetes stack. Now, Kubernetes is one of those platforms which will allow you to scale your algorithms to as many GPUs as needed for training. However, it's hard to get the linear scaling efficiency with the increase of the underlying infrastructure. And that's because there are a lot of overheads that comes in when the machine needs to communicate with each other to synchronize the gradients. And that ends up kind of being very expensive. Now, that's where SageMaker comes into the picture. Now, SageMaker is a fully managed service which helps build, train, deploy the machine learning models. and it provides a very specific topology on AWS. So the algorithms could fully utilize the underlying infrastructure in a managed way, and the network is highly optimized that is used for the machine intercommunications, and that actually makes your entire model training process much faster, much stable, and much fault tolerant. Now, SageMaker, being it a managed service, it does provide its own flavor of distributed libraries, which are called SageMaker Distributed Parallel and Model Parallel. And those are highly optimized and could be integrated with your existing PyTorch, TensorFlow, or MXNet code with a very least amount of code changes.
Awesome.
Yeah, that sounds great. So let's jump into this demo.
So to demonstrate the concept of distributed training using Kubernetes and Kubeflow on AWS, we've prepared this hybrid architecture diagram, which allows us to not only utilize the self-managed approach of training distributed models on EKS using Kubeflow, but also be able to seamlessly submit workloads to the SageMaker runtime. I'm going to focus on demonstrating the self-managed part of this architecture, and then I will pass to my colleague Kanwal to demonstrate the SageMaker part of this architecture. So just a little bit of a background to set up distributed training on Kubernetes on AWS. A lot of customers like using our managed Kubernetes service, EKS, the Elastic Kubernetes service. And to do distributed training, you having an EKS cluster is sufficient. However, deploying Kubeflow on that cluster provides not only an integrated development environment that ML scientists can use on the platform, but also the ability to automate workflows of distributed operations. Because training is typically not the only step in that workflow, Kubeflow provides that opportunity to perhaps set up a pipeline where you first download the data, then prepare it for training, after that run distributed training, and post-process the model and perhaps deploy it for inference. What we'll demonstrate today will focus on the distributed training part on Kubernetes, but the idea of this architecture is really to provide a holistic solution which allows customers to utilize both self-managed infrastructure as well as fully managed infrastructure like SageMaker. So with this,
I was going to say, I love the buildup. I'm excited to see it.
I am excited to show it as well. I will just quickly share my screen here. My command line shows that I have a cluster with 2 nodes, and I'm going to run a distributed training job on this cluster. These happen to be G4 DN nodes with NVIDIA T4 GPUs. I will use the PyTorch training operator to submit this custom training job, and I'm just going to show what this job looks like. This is the job manifest. Basically, it is a PyTorch job which has this name, and it has one master node configured, which is going to utilize a single GPU. We will use Torch distributed run to train an ImageNet model. And if I scroll down, we'll also see that there are 2 workers that will be distributed among these 2 nodes. Each of them will use a single GPU. So in total, we're going to have 3 nodes participating in this distributed training, and they will train an ImageNet model. So to start the training, I can show that first there are no training related pods running in my cluster at this time. If I apply the ImageNet manifest for this training job, a PyTorch job gets created, and I am now seeing that pods in my cluster are initializing, and they become running. I will use a utility called Kubetail to aggregate the logs of these training pods, and each of them will come up with its own color. So we can see that the 3 pods are working together to perform this distributed training. With this, I'll pass on the screen to my colleague Kanwal to talk about how this works on the SageMaker side.
Thanks, Alex. So yeah, let's see how we can really submit the same distributed training now to SageMaker. And I'm going to use AWS specific Kubeflow distribution, which actually adds value over open source Kubeflow through managed service integrations like RDS, Amazon Cognito for authentication, and many more. So this is the Kubeflow dashboard that we see here. And I'm using Jupyter notebooks, which we can spin up from here to really create the Kubeflow pipeline, which will actually allow us to automate our machine learning workflow. And that pipeline will leverage SageMaker in the background for distributed training. Now, we're going to use a complex, a very simple neural network, and we're going to train that with the Cypher10 dataset. And if you see here, we're going to use open source PyTorch libraries, which is PyTorch GDP, which comes with a distributed package. And this code we're going to integrate with the Kubeflow pipeline using the Kubeflow pipeline SDK, and it provides decorator functions to allow you to create those pipelines through the Python specific language. Now, just to show you here quickly, we are using SageMaker component for Kubeflow pipeline, which actually abstracts away the SageMaker complexity of API calls and lets you just provide your SageMaker parameters in the form of these variables. And if you see here, I'm specifying that I want to run the distributed training on SageMaker on 2 EC2 instances, which are of type P32X large. So that information is here up here. So once I submit this pipeline, it's actually going to create a visual graph, which you can monitor and see whether it has been successful or there are any failures. And these graphs are pretty intuitive, and you can see that it's kind of 3 steps that it is following. One is running a training job on SageMaker, and you can click on that and actually can go in and see whether the training was successful and what were the input parameters of this particular component, which basically is a container running in the background, and what are the outputs that the SageMaker training process has generated, right? So you can, and it points you to the S3 location where your model artifacts will get saved, or any other tensors that you would like to save as part of your training run. And there will be the logs as well, which you can go and see on what is the status of your training run on SageMaker. Now, apart from your training run, which you are doing with SageMaker, you can actually also monitor your metrics right from the Kubeflow dashboard using TensorBoard. So the training which is happening on SageMaker, it's actually outputting all the tensors in S3, and the TensorBoard is pointing to that S3 bucket and emitting these wonderful graphs. So if you see here, I'm actually printing out how my training accuracy is improving with the number of training iterations, and I have run various different experimentation with different learning rate. If you see, if my learning rate is too small, there won't be any improvements in my accuracy. But then if I tune my parameters, my accuracy will tend to get better. And similarly, you can use the logs for loss metrics as well.
Nice. No, that's awesome. And I love, unfortunately, we're getting close to time here, but I love the hybrid architecture and then also the hybrid demoing. I think that was a great way to show how both architectures work. But yeah, thank you all for joining us at AWS On Air. It was so great to meet all of you, and I learned a ton today. So folks that are watching, please stay tuned for some more sessions here at Reinforce.